Hello everyone. So let us continue with the problems based on line integrals in vector calculus. So if we look at our next question, so question number 3, the question says in the first part what you are to do, you are to show that vector f which is equal to 2xy plus z cube into I cap plus x square j cap plus 3x z square k cap. Firstly, you have to show this is a conservative field. So this is first part. You know what to do for this. You have to take the curl of the vector, and if that comes out to be 0, that becomes your conservative force field. Okay, in the next step you are to calculate the scalar potential. So you also know if your force field is conservative in nature, that means a scalar potential is always associated with that. So we are to determine that in this second part. In the third part, we are to calculate the work done in moving an object in this field. Given the points 1, -2, 1 to the point 3, 1 and 4. So this is our question. So let us have a look at its solution. For the solution, first of all, let us prove that this is a conservative field. So now for that our vector f is given to be this 2xy plus z cube I cap plus x square j cap plus 3xz square k cap. So what we are to do, we are to calculate the curl of this vector, and you know very well how to calculate this curl. So we'll do the determinant, writing I cap, j cap, k cap, and then del by del x for this del by del y and del by del z, and corresponding to the vector f we will write this quantity. So it would be 2xy plus z cube, it would be x square, it would be 3xz square. So when you solve this quantity, this would become equal to I cap. So the derivative here, this would be equal to 0, and then the derivative here with respect to z is also going to be 0. Then minus j cap. For j cap, you will apply this operator onto this. So this is going to be 3z square minus you will apply this operator onto this function, right? So you have again 3z square. And for k cap, what you will do, you will apply this operator onto this function, so that is equal to 2x minus you will apply this operator onto this function, so it is also again equal to 2x. So in effect, you see you have 0 I cap plus 0 j cap plus 0 k cap. So this is actually the 0 vector. So therefore your curl of the vector f, that comes out to be 0 vector. Therefore you could conclude that vector f is a conservative force field. So this is what we wanted to prove in this first part. For the second part, we wanted to calculate this associated scalar potential. Now if you remember the definition for scalar potential, what is that? So we knew that if f is a conservative field, then the quantity we can write this to be the gradient of some function phi, which is the scalar field, and this is actually known as this phi, this is known as the scalar potential. So we are to calculate what is this phi. Now we know what is f. F is given to be 2xy plus z cube I cap plus x square j cap plus 3xz square k cap. This is the vector f that is given to us. So this is equal to the del of operator, del of the scalar function phi. So this quantity is equal to del phi by del x I cap plus del phi by del y j cap plus del phi by del z k cap, right? So now you have on the left hand side a vector quantity, on the right hand side also a vector quantity. and these two vectors, they are equal. So that means the component for I cap is equal. So that means from here you have 2xy plus z cube. This is equal to this thing. So this is equal to del phi by del x, and the component of j cap is again equal. So you have for j cap we have x square is equal to del phi by del y, and for k cap similarly we have this thing is equal to this thing. So we can write 3x z square is equal to del phi by del y. So we got these three equations where we are to determine what is phi. So what we can do here, we can integrate these with respect to x, y and z. So once you integrate the first equation, so let's see what do you obtain here. Integrating this, you obtain the value of phi. Now you are integrating with respect to x, so that means you are keeping y and z as constants. So when you integrate here with respect to x, you have x square y and plus xz cube. Why? Because this is treated as constant, this is treated as constant, this is also treated as constant, and moreover we have to write the constant of integration. Now the constant of integration would be some function of y and z. Why? Because we are integrating with respect to x, and your phi, that is a function of x, y and z. So that means the remaining constant would consist of these functions. So this is one value. For the next value, if you integrate this, you will obtain phi, that is equal to, now we are integrating with respect to y, so that means you will have x square y, and also you have some another function, say g, of the remaining quantities which are x and z in this case. So you have the function of x and z. And for the third case, when you integrate this, you will have phi, that is equal to, now you are integrating it with respect to z, right? So it would be, these would be treated as constant, so it would be x into z cube, right? X into z cube. So plus the constant of integration, this would be another function consisting of x and y, because we are treating them to be constants. So you obtained these three equations. So now we are to determine by looking at them what are these constants. So that means for sure our phi will contain all these functions. So phi will contain x square y is coming here, so that means here it should be function of x and y, right? So that means this h of x y should be here, because it should also come in this function. So that means you have x square y here for sure. Next you have this term xz cube. Now xz cube is coming here and here, so that means this has to be xz cube. So that would be xz cube plus the other quantity that you are getting as this function of f of yz, which you do not know as of now. So you can call this to be some constant c, because there is no other constant coming up here. So c is some constant quantity. So this is how you obtain your scalar potential, right? This is the second part. For the third and final part, let us move on to our question. It says that find the work done in moving an object in this field from the point 1, -2, 1 to the point 3, 1 and 4. So basically what you are doing, you are to calculate the work done. Now there are two ways. Either you calculate the integral of this particular function with respect to dr along the given curve from this point, or what you can do, you can substitute these points in the given scalar functions. So that is easy. So for the third part, the work done could be calculated when you substitute the value of the given points 3, 1, 4, the final position, minus the initial position, that is 1, -2, 1 in the given value of phi. Now you obtained this value of phi as this one. So when you substitute the values of x as 3, so you have 3 square, the value of y as 1 plus 3 into 4 cube plus c. This is for first part. For second part, it would be 1 square into -2 plus 1 into 1 cube plus c. So when you solve this c and c, that will cancel out. So you have 9 plus this would be equal to 192, and you have plus 2 plus minus 1. Yes, minus 1. So this will come out to be 202. Right? Yes. So this is the work done that has been used to move some particle moving in this field from the point this to this point. Right? So I think you understood all the parts well. Now let us move on to our last and final question. So the next fourth question here is a fluid motion is given by the velocity of the fluid, that is given to be y sine z minus sine x I cap plus x sine z plus 2yz j cap plus xy cos z plus y square k cap. Now this velocity is given to you. There you are asked, is the motion irrotational? This is the first thing. Now what do you mean by irrotational? Just remember that. Also they are asking, if so, if the motion is irrotational, find the velocity potential. So this is the next part. So let's have a look at its solution. So first of all, we are to check whether this motion is irrotational. Now if we are to check the motion is irrotational, we'll check for this vector to be irrotational, and by irrotational we mean that the curl of this vector should be equal to 0. That means there should be 0 vector. That means there should be no rotation at all. So we'll calculate the curl of this vector. That is very simple. You already know how to calculate curl for vector v. So that is del cross the vector v, right? So it would be equal to calculating the determinant of I cap, j cap, k cap, del by del x, del by del y, del by del z, and the components of vector f, they are given to be y sin z minus sin x, and it is x sin z plus 2yz, and for the third part it is xy cos z plus y square. So we can compute the determinant here. So for I cap, you have to operate this onto this. So let's see, what do you have? You have y cos z plus 2y, and then you have to operate this onto this. So I'm sorry, the other way around, this onto this, right? Because this is the operator. So we have x cos of z minus 2y. So this is I cap. For j cap, you have to apply this onto this. So that would be y cos z only, minus you have to apply this onto this, right? So you have y cos z, yes, that's it. And for k cap, what you have to do, you are to apply this onto this. So that means sin z, and this onto this. So that is also equal to sin z. Now when you simplify this and you solve this, so you see this and this cancels out, everything cancels out here. So you have 0 I cap plus 0 j cap plus 0 k cap, which is equal to 0 vector. So therefore you obtain the curl for vector v as equal to the 0 vector. Therefore the vector v is irrotational in nature. If this vector is irrotational in nature, so that means the given motion is also irrotational. So this was our first part. For the second part, so if the motion is irrotational, if this quantity is equal to 0, so that means you can say the velocity field v is the conservative force field, right? And if this is the conservative force field, in that case whatever is the quantity v obtained written as the gradient of some function, scalar function phi, that phi is the scalar potential. And basically it is we are calculating this quantity for velocity, so we can call this to be the velocity potential. So let's quickly see what is this quantity. So you are given the vector v. So what we are doing, we are calculating this. We are given vector v as y sin z minus sin x I cap plus x sin z plus 2yz j cap plus xy cos z plus y square k cap. This is equal to del of phi. What is del of phi? That is del phi by del x I cap plus del phi by del y j cap plus del phi by del z k cap. Now these are again two vectors, so we can equate these vectors. So equating this I component, I cap component, you obtain y sin z minus sin x, that is equal to del phi by del x. Equating the y component here, we will obtain x sin z plus 2yz, that is equal to del phi by del y. And equating the third component here, this one with this one, we obtain xy cos z plus y square is equal to del phi by del z. Right? So this is what you obtain. Now here, either you are to integrate these in order to, the next task here is we are to find phi solving these three partial differential equations. Now it is up to you how do you want it to solve these equations. One way is to integrate these equations as we have done in the previous question. Another way is you can make an exact integral out of it. So how can you do that? You know, you can write the d phi, which is the complete derivative of phi, as the function, because phi is a function of x, y and z. So you can write that to be del phi by del x dx plus del phi by del y dy plus del phi by del z dz. Now you have the values of these quantities from these equations, so you can write it over here and try to make this as the complete integral. So let me write down this value first. So it would be equal to y sin z minus sin x into dx as such, plus the value of this quantity. So it would be x sin z plus 2y z into dy plus this quantity. So this is equal to this. So you have xy cos z plus y square into dz. So now what you are to do, you are to make this into the complete integral. So we can separate out these terms. So I can write this to be y sin z dx minus sin x dx plus x sin z dy plus 2yz dy plus xy cos z dz plus y square dz. Now you are to inspect all the terms and see whether you could make the complete integral out of any of these terms, right? So this is up to you. Now if you look at this term, here you are seeing the derivative of x and the term y sin z. And if you look at this term, you are seeing the derivative of y and x sin z is as such. So that means you could write the complete derivative of this term. And moreover, you have this term also when you are seeing x and y as such, and the derivative of sin z, so which is cos z into dz. So basically if you write this, all these three terms to be x, y, sin z. So if you solve this, firstly you will write x as such, y as such, the derivative of this would be cos z dz. Then x as such, the derivative of y would be dy sin z as such. plus the derivative of x would be dx, y and sin z as such. So these are these three terms only. So you understood my point? How can you make this complete derivatives by inspection? Okay, so now we have to look for another terms. Now this term could be written as the complete derivative of cos x, because when you differentiate cos x, it would be sin x minus sin x into dx. And moreover, for these two terms over here, one is when you this shows here the derivative for z has been performed, y square is as such, and here the derivative for y has been performed, z is kept as such. So that means you can write this to be the derivative of y square into z, right? So that when you differentiate this, you obtain these two terms. So this is the complete derivative. Now because you know derivative is linear in nature, so you could club all these terms. So you can write this to be xy sin z plus cos x plus y square z. So this is your d phi. So because we are to calculate phi, what we can do, we can integrate on both sides. So when you integrate, you have the value of phi as equal to x y sin z plus cos x plus y square z, and moreover we also have some constant of integration. So this is the corresponding velocity potential that we were asked to calculate. So I hope you understood this concept well. The questions are pretty simple. All you have to know is the formulas. So I'll see you next time with the surface integrals. Have a nice day all of you. Bye bye.